Hi everybody, welcome to our institutional seminar here at the Department of Statistics. Our speaker today is Professor Carlos Tadeu Pagani Zanini. He's a professor at the Universidade Federal do Rio de Janeiro in Brazil. Carlos holds a PhD degree in statistics and data science from the University of Texas at Austin. There, his advisor was Professor Peter Mueller, who is a renowned researcher in the field of Bayesian statistics. His research interests range from Bayesian statistics, biostatistics, mixture models, Bayesian non-parametrics, dynamic models, deep learning, and neural networks. The title of his presentation is Deep Neural Networks for Object Detection with applications to the preservation of marine ecosystems. So at the end of the presentation, the audience will have around 10 minutes or more or less 10 minutes for questions. You can ask in either English or Spanish, even Portuguese if you will. So Carlos, thank you again for accepting the invitation and go ahead with your presentation.
Well, thank you, Jonathan. So I'm very pleased to be here and to be giving this talk to you. Let me try and share my screen so that you can see the slides.
Yeah.
Do you already see it? Or?
Yeah. Just give me 1 minute here. I'm just going to set this. Okay. Yeah, I think we're okay now, and yeah.
We're good. You can see my screen now.
Yeah, we can see your screen. Yeah.
Oh, okay. Yeah. Awesome. Well, thank you very much, Jonathan, again, and thanks for the opportunity. And so, as Jonathan said, my name is Carlos, and I'm from UFRJ. I'll be talking with you a little bit with two of my works that I have done with two students of mine, Igor Nunes Patricio and Thiago Stephen, both from UFRJ, on deep neural networks for object detection. And these two applications are in the context of preservation of marine ecosystems. So for today, I'll be talking first about the problem of detecting objects of interest in image and videos. So this is the context of object detection. Then I'll be presenting the motivating applying problems involving preservation of marine ecosystems. Then I'll go very briefly through an introduction to neural networks for classification. So I'll be talking about the perceptron, which is one of the building blocks for the deep neural network models, and also through multi-layer perceptron, which is a generalization of the concept of perceptron when we put them into multiple layers to form a model that is more robust. And then we go over convolutional neural networks that are used a lot for images. And then finally, but this is all for the context of classification. And then after that, I'll be talking about neural networks for object detection specifically. And I'll be focusing mostly on this one, which is called You Only Look Once, is the name of the architecture. And we just say YOLO is the name of it. And then I'll be going over some results on applied data with hopefully cool images and videos that were done by Igor and Thiago, which were my students and the works on applying this methodology to the different data sets. So just so you guys know a little bit about the problem up front and what we're trying to solve. So we'll have basically two data sets. In the first one, we want to detect this type of starfish named crown of thorns. So the crown of thorns, which we'll be calling cod for shorter, right? They are a starfish species, and they feed on coral in the reefs. So the problem is that the human action on nature may cause superpopulation of cods, and this can cause serious problems to the corals because these are species that feed on the corals and also on the local environment. So for this application, well, this is a cable competition data set, and we have real videos taken on the Great Barrier Reef, which is a very big reef in Australia. If I'm not mistaken, is the biggest one, but I'm not 100% sure about that. But it is a very big reef that we have in Australia. And then for this one, we have 3 videos, and then we'll treat each frame of the videos as images, and we'll feed the model to work on those. So we have a training video, a validation video, and also test video. So just so you know, these are RGB images. This is the original dimension. It's 1,220 and 80 pixels by 720. So this is high correlation images. And then the point is that we'll have very small COTs that are pretty hard, I think, to recognize because they are taken from far away distance. For example, here we have one of those images from, it is just a random frame from the video, from one of the videos. And I'm showing you now. I'm not sure if you guys can recognize, if you guys can reckon it, but like here, you can see that there is one such COT. It's like a circle, right? And then it has these little spiky things here. And there are several of them in this image, but they are a little bit hard to spot. For example, there's one here, and so on. So if you guys want to see all of them, here they are. So you can see lots of them, and it's a very challenging problem. So what we want to solve is we want a model that receives this as an image and outputs this, meaning the location and also these boxes that go around the object. So this is the so-called object detection problem. So it's pretty complicated, and that's why we are doing neural networks to solve this. On the second data set, it is a little bit different. We are trying to detect trash in deep ocean floor. In this problem, we have remote operated vehicles, or rods for short. And those are just, you can think of them as robots that go on the seafloor and record videos on it, searching for new species or for trash in the ocean. There are some robots that actually can collect trash or specimens from the deep sea floor and then take it to the surface to be analyzed. So for this problem, the main difference is that we are interested in 3 classes, which are bio, meaning anything that is alive, basically. It is a little bit subjective here, so you guys will see it later. But we are mainly interested in detecting trash in the deep sea ocean. And also we have the ROV itself. So sometimes the robot films parts of itself. So we have basically these 3 different classes that we want to spot and also differentiate which one are there. Right, so these are like 5,720 images. The dimensions are much shorter from the other data set, and they come from this data set by Photon and al. And they were published in the International Conference Robotics and Automation, which is called ICRA. So I'll be calling ICRA or ICRA to refer to this data set. So you guys can see a little bit what it's about. It's like this. So these are the images, like one of the images that we have. They are also from videos. And we want to detect if it is raw, if it is a bio, or if it's plastic. So here you can see part of the robot. It's a little bit hard of a problem because like here you can probably see this is also a part of a rod, but the model here just captures this little part. And also on the right side, I wanted to exemplify to you that this object detection field is a little bit subjective because there is no single way of marking those images. Depending on the context or on the image, yes, there's only one possible way to mark the squares, but we could have like more squares here to separate these pieces of trash. Also, we can arguably include this one as well that was not included. So this was what was marked in the data set. right? So this is also to show that it's a supervised problem where we have to provide not only the images, but we also have to provide in the data set the location of these boxes and also the class that the box belongs to, right? So it's a supervised problem. Okay, so this is the setup and what we want to solve. Now I'll be explaining shortly what is the model that we're trying to fit. So these models are, which we call deep neural networks, they all build from this single perceptron. What is this? This is just a function, right? So if you have ever seen like this kind of scheme, this is the perceptron represented in a graphical way. So here we have the inputs, which are the data. In our problem, this x1, x2, xn is the intensity of the pixels that form the image, right? So so each one of these is 1 pixel, and the value of x1 is how intense is that pixel. So if it is grayscale, then the bigger the number, then the closest it is to a black spot. And the lower the number, the closest it is to 0, for example, right? So this perceptron, it receives as inputs this x, and it has weights associated to them and also a bias. So these are parameters of the model, and it tries to estimate them. So basically, the perceptron operates in 2 steps. First, it is applied an affine function to the inputs. So we have age, which is just x1, the first pixel, times the weight, w1. And then we do x2 times w2. And we go until we get to the last pixel, is xn times wn. So it is simply a linear combination plus a bias that is going on here. So this is simply a linear combination of covariates where we have an intercept, if we talk about it in statistics terms. So this is the first part. It's just an affine function of the inputs. Then the second step is to apply a nonlinear activation function, which here we call f, which takes h as input and then outputs f of h. So this first step here of the neuron or perceptron will transform the inputs in an affine function, and then it will apply a nonlinear function to it. And after that, we'll have the output, right? So for the perceptron goes up to here, basically, right? So what is the objective of the perceptron? Is to map the inputs into like a single number, let's say. And this number, this is just a deterministic transformation of the inputs that will qualify my stochastic variable, which is the response y. So it is a regression setup, right? So we have the y as output and then x as input. So the output of this activation function is going to be a parameter in the distribution of y. So this is how we link the statistical or stochastical modeling to the neural network part. It is simply a function from the neural network is simply a function from the inputs into a parameter of a random variable that will characterize the stochastic behavior of a random variable. And then for these activation functions, which are the nonlinear functions, what are them? Well, so these functions can be almost anything, as long as they are nonlinear. So, for example, there is this very famous function, which we call ReLU, rectified linear units, which is the maximum between 0 and x. Here is the graphic of the ReLU. It is clearly a nonlinear function. We can also use a sigmoid, which outputs probability, and it's suited for binary classification. Why is that? Well, because the sigmoid is 1 over 1 plus e to the power of minus x. This is what we call the logit link, right? In the logistic regression, for example. Here is the plot, it's the graphic of it. So since the sigmoid outputs something between 0 and 1, it is used a lot as an output of a classification problem, right? Which is one of the steps of the problem that we want to solve. So for example, if we show an image of a cod, like a starfish, we want the model to output a 1, indicating that it is indeed an image of a cod. If it outputs 0, it's because the model thinks it's not a cod, it's something else. Or if it is closer to 0, if the output is a probability close to 0, then we're going to decide, okay, it's probably not a cod. If the output is close to 1, we'll say, okay, it's probably a cod, right? And then this will work as an output for the first problem, where we are interested in only identifying this specific starfish. But for the second one, where we have more categories than 2, we have 3, right? The trash, the bio, and also the rod. We will need something like the softmax. So the softmax function receives as input x1 to xp, and then it exponentiates each one. So it will be exponential of x1, exponential x2, xp, and then we'll normalize all those. So this is going to be a probability vector, meaning that its entries are between 0 and 1, and the sum is 1. Okay, so this is for multiple classes, and this is usually for classification using one, having only 2 classes. And this other one is for 3 or more. Okay, so I just want to give a little bit more motivation before I move on to the more complicated models. So we are all, if we are all statisticians, we are all very familiar with the notion of the logistic regression model. What we have is yi coming from a Bernoulli with a probability of success in pi. And then what do we do? We do pi equal to a sigmoid applied to this affine function of, let's say, 2 covariates. Let's say we have 2 covariates, and we want to predict if their label is 0 or 1. Like 1 is the ball and 0 is the triangle. So in this problem, you can see that it is exactly the perceptron, right? So if we draw it in that notation with the little balls and the little edges here, we can see that it is a perceptron, right? Because it multiplies W1 with X1, W2 X2, B, and 1, combines them into a probability PI, which is the sigmoid applied to this. And then we go ahead and put this probability inside of the the probability of Y in the probability distribution. So we say this probability determines which Bernoulli it is. So this is all to say that logistic regression is a particular case of a perceptron, right? So the perceptron is the same thing as a logistic regression, right? If we choose the sigmoid as the activation function. And one little thing more is that we want to emphasize that the decision boundary for logistic regression, or for one such perceptron, is a hyperplane. How do we know that? It's just we define the decision boundary as the space in X and in X1 and X2 that will be indecisive about if Y is 1 or Y is 0. So if I give you a point here in this line, the model is not going to be able to say what point it is, if it is a triangle or a ball, because it's in the frontier. So from this relation, we can easily see that the frontier is a hyperplane, because we are in doubt of what the output is when p is equal to 0.5. Then we are equally uncertain about if it is a 0 or a 1. So the space in X that makes this equal to 0.5 is the space in X that makes this equal to 0. And this is the equation of a hyperplane. Here it's just a line, but because it's on 2 dimensions. But if we have more, then we have a hyperplane. And so this simple perceptron thing passes through a hyperplane in space and tries to classify the output. So here in this model, we have a generalization of a perceptron, which is the multi-layer perception. And here I'm showing you just a model for binary classification. So what is the difference? The difference is that we have several perceptions now. So this is one perception, this is another one, this is another one, and so on and so forth. And they are organized in these sequential layers so that the input serves as input for this perception and this one and this one. And then the output of these perceptions work as input for the perceptions in the second layer, and then those go to the last layer, which has to be a probability if we are talking about a binary classification to be fed into the distribution of Y, right? So this is a generalization of the perception where we use multiple perceptions in a multi-layer framework. And then here is the application. So it is the equations that define the model. So you can see it's basically a composition of functions. So this is all complicated function, but it is a function of xy going to a space of probability, and then this probability characterizes the distribution of y. Okay. So and then why do you want to do this? What is the motivation of having more perceptions? So this is what the perceptions do. Remember that each perception passes through a hyperplane through the original space. So here we have the different x1 and x2 for several points, and the aim is to classify the yellow ones from the blue ones. So we can see that no hyperplane is able to classify here, but we can combine this hyperplane, which is arguably somewhere like here, with this other hyperplane, which is here, like this one is about here, this one is about here, and this is probably redundant because it's doing like the same function as this one, but it's okay, it's just redundant. So if we combine the different hyperplanes, we can get a much more flexible region of classification, and then we can have these different features, right? So it is not exactly combining, it is not exactly superposing the hyperplanes, because you don't see an actual triangle here, because the functions are smooth, the sigmoids are smooth. So you can get this smooth shape around here. So the point is, I want to illustrate that if we combine the different perceptions, we have much more flexibility into doing the classification, okay? So, and then here you can play around in this website. It's very nice. You can have several examples of points, and then you can build your own network and put more neurons and less neurons. It's really nice. I really recommend you that you both that you all check this afterwards. So this is the empirical justification. But if you prefer a more formal one, then there are some theorems in universal approximation theory that says that these deep neural networks can basically approximate any measurable function. So any Borel measurable function can be approximated, even if we use a single hidden layer. As long as we can put more perceptions in those layers, we'll be able to approximate well enough anything. So if one layer is necessary, then why these deep models will put more layers on top of each other if one is enough, right? So the answer for this theoretical question is given. For example, there are many papers that talk about it, but this is one of them that says that if we do it in sequence, like having lots of different layers, we will use much less parameters, and so we will need less perceptrons than if we would put them all into one single layer. So if we have a finite budget, meaning the number of perceptrons, it is better to put them into a sequence of layers than to put them all into one layer. So this is the motivation why we want to build these deep models, and why the deep models are more flexible than the shallow models or the logistic regression, for example. Okay. So this is the first part for classification using the multi-layer perception. Here we have the way of doing inference. So how do we make inference in this model? It is not hard. So we actually, I mean, it is hard in practice because of some limitations. I'll be talking about this later. But theoretically, we have a likelihood, right? Because we have this Bernoulli model given the model parameters, which are the weights and the biases to be learned. We can simply do the log likelihood and then maximize it doing maximum likelihood estimation. In these problems, we have so much data that usually we're not interested in quantifying certainty of these parameters. Usually, just the maximum posteriori or the maximum likelihood estimate is good enough for our purposes. And actually here, we only have a point estimate for all the parameters. We're not concerned about confidence interval for the parameters and none of that business. We only want to have a model that is able to generalize and to spot these animals and these objects of interest in different images. So how do we go about it? So we write the log likelihood or minus the log likelihood, it doesn't really matter. Let's say it's the negative log likelihood. And then we do gradient descent, which is basically applying the gradient into the minus log likelihood and do a gradient step. So here we actually don't need to pass through the entire data set, meaning y equal to n. We can go over a smaller data, like if a smaller batch of data. So since we can pick, for example, we can choose, let's say, for every iteration, I don't need to feed the entire collection of data to the model. We can do it in only, let's say, 10 images or 5 images or 100 images, and then calculate the log likelihood on those 100 images, as long as they are chosen at random. If I randomly pick, let's say, 10 images, and then calculate the log likelihood of the model on those 10 images, this is going to serve as an unbiased estimate of the entire gradient. This is the concept of stochastic gradient descent. Right? So as long as we have an unbiased estimate of the direction given by the full gradient, the algorithm will converge. So here we have 3 examples. So one is let's say the full gradient. It points to the optimal direction, right? And then we converge pretty quickly. But if we feed less data than all data that we have, then we're going to start having these more wiggly trajectories around the optimum, but it will converge. So this is when the batch is not that small. So usually you're going in the right direction. And then in purple, you have the case where the size of this subset of data that I'm feeding at every iteration is very small. So then you wiggle a lot, but in any case, you will converge. So what happens is that maybe the trajectory fluctuates more. Right? So the point is that if we sample just a little, just parts of the data, it is much faster than trying to pick up the optimal direction, because one arrow like this is very expensive to compute, because we have to go over those 10,000s of images and then apply the network into all of them, which is very expensive. So instead, we want to do it with few data at every iteration. Okay. So just to make things maybe a little bit more clear, so what I'm telling is we'll have, so how will this work with this model setup work? So we have the real image in the context of classification. So we're not interested right now into putting the box around it. So we just want to say if it is a cut or not, let's say. So we feed an image. So this image enters the model as a 3D tensor, like RGB, where we have the pixel intensities. It goes here as the input layer, and as the output layer will have a probability that is trained to be close to 1 whenever the y is 1. So since this is a cut, then we say y is equal to 1, and then the model will learn that when it sees an image like this, it needs to output p close to 1. On the other hand, if there's no cut in the image, then the model will try to learn that y is equal to, the model will receive y equals 0, and it will learn that the p that it needs to output needs to be close to 0, right? So this is the setup. So this is how we interpret. So here it's just like we destroy the image, putting the different pixels here aligned. Okay. So to fit this to the model, we have to get rid of the spatial structure of the pixels, right? Because we have to align them, and so it is not the best way of entering with the data to the model. So we want the model to actually see the image and actually learn how to recognize characteristics whenever, like in whatever space the characteristic is. So here you can see the pointy spots in the starfish. So what we want is to have a structure that will recognize, let's say, these little spikes wherever they are in the image. So we want to feed the entire image to it, and we also want to recognize the patterns wherever they are in the image. So for that purpose, we have the convolutional neural networks. So how would they work? Well, they are, in some sense, very similar to the perceptrons. So associated to the network, we have a kernel, which is a small matrix of weights. And these weights work in a very similar way to the regular perceptron. What they do is they will apply these weights, which are learned by the model, they are parameters, and they are applied to the input image. So W7 will be applied here, W8 will be applied here, W9 here, and so on. So we will have this first 3x3 squares outputting this square here, therefore transforming the image into this reduced image here. So why do we want to have that? Let's see. So just to clarify, this guy is a perceptron, pretty much like the perceptron I showed you before. But the point is that this guy will only look at this 3x3 square. So it will have these 9 weights here to be learned. And then I will apply these 9 weights into this part of the image. Then I will move to the next perception here. So the same weights will be applied to this region of the image, therefore outputting this perception. So once I see the entire image, I will have the transformation here, right? So this is what the convolution does. Each one of them is a perceptron, and they share the same weights. Why is that useful? So that is, I think, that's the question that begs answer, right? Well, they are useful because with very few parameters in these kernels, you can get pretty nice structures to be recovered by the model. For example, we can get edge detection by taking a simple kernel of dimension 1x2, where let's say the first one is -1 and then the second weight is 1. If we apply this to every little piece of the image, we'll actually calculate the difference between consecutive pixels. So if there is an edge in the picture, like from here to here, then this difference is going to be significantly different than 0. And then you see this line. But if I pick two neighbor pixels inside of the dog's fur, they will not differentiate a lot from itself, right? So it will output this 0. So in this picture, we'll have that the gray is 0, then the black is 1, let's say, and then the white is 0. Okay. So with this kernel, we can recognize the edges of the image, right? And then it's just 2 parameters, and they are applied to the entire image. So, and of course, these kernels can vary in dimensions, and it's usually done in 3x3 or 5x5, sometimes 7x7, to recognize richer patterns in the image. Just so you guys can have an idea, here I'm showing one such convolutional neural network, which is called the LeNet-5. It is pretty old, right, from 1998. So this was one of the very first convolutional neural networks used to recognize, in this case, numbers. But for this illustration, I'm illustrating it with a letter here. But we can say that we can think that is 10 letters, right? So the model is trying to recognize if this is an A or a B or a C. Okay, so how does it work? So I have one first layer of those convolutions. So this is one transformation of A done by the application of one kernel into the entire image. Then it will output this, which is an image of a dimension slightly smaller than the original, right? So if I apply another kernel, I'll have this guy here. So it is a different transformation from the first image, and so on and so forth. So here we have basically 6 kernels being applied to the image, and then we'll have these 6 different transformed images. Here we have image reduction step, which is done by max pooling. I'm not going to go over details, but you can think of it as a convolution as well, if you will. It's not exactly a convolution, but it is similar. And then on the second step, we will do the same thing, apply kernels again, but then we'll apply kernels to these transformed images, therefore recognizing patterns into this transformed image, these transformed images, and so on and so forth. At some point, we'll have small transformed images, and then we feed them into a multilayer perceptron model. So this part is a multilayer perceptron. It is not represented here, but there are small circles here representing the perceptions. And then you go to the end. Since this is originally illustrating the MNIST problem, we have 10 classes, which are the digits. So it's 0, 1, 2, 3, 4, 5, until 9. So you have one output for each digit. And since there are 10 digits, then we have 10 here at the end, right? So this is how we combine. So when we talk about a convolutional neural network, we are talking about a convolutional structure with multi-layer convolutions, followed by an NLP model, which is a multi-layer perceptron. We can also represent the very same architecture in this way with the cubes. So it is the same as this, but instead of with this representation of multiple squares, I'm grouping them together into this cube. But it is the same thing. It's the very same thing. And so I'm just showing you this representation because it's going to show up later. Jonathan, do you mind letting me know how much time do I still have?
Well, I think maybe, let me see, let me do the math, maybe 15 minutes.
Okay, cool. So the last slides are all images, so I just want to make sure I explain the architecture. But thank you. Okay, so now we're going to talk specifically about object detection. So on, I'm just telling you how to identify the different classes. So these networks, all they do is classify images. They don't tell where the image is, like where, if I show you a picture of a cot, it is one thing to say, okay, there is a cot in the image. It is a different thing saying, okay, there is this object of interest in the image and it is a cot, okay? So classification is a part of the problem now, but it is a problem within a second problem, which is detection. So we want to say where the object is, and we want to say what class it belongs to, okay? So I'm just showing you here in the context of one of the 2 data sets that we have. So we want to output both things, where the object is and what class it belongs to. I'll be showing you results based on this model, which is YOLO. It stands for You Only Look Once, by Redmond, 2015. This was the first paper in this class of models. Nowadays, I think the most recent version is, I don't know if YOLO X, which stands for 10, is the most recent one, but it is the most advanced I know of. So there are lots of versions that came after this one. I'll be explaining just the first one because the model is really complicated. So I don't want to be complicating too much. So we'll just grasp the idea of how it works. So YOLO, what YOLO does is it divides the image into a grid of cells. So here we have the entire image, and then we'll divide this into this 1, 2, 3, 4, 5, 7 little squares by 7 squares. And then what do we do? Each square of this will have B bounding boxes associated to it. So here I'll have a bounding box, which the center is inside of this little square. Here I'll have other B bounding boxes with the center being here, and so on and so forth. So here we'll have all the bounding boxes. So you can see that there are a lot of them, right? So there's one here, there is another one here. There are lots of them clapped around here, and lots of them here. But we don't want that, right? We want to have only these 3 ones, which are detecting the image. So what the model does is afterwards, it will learn which boxes are redundant, and it will eliminate it. And then we'll have only one, which is the best box, right? So it is a model that does all of this in one run. So this was the novelty of it. So it just receives the image, divides it into grids, and then outputs a box. And then we'll see how it works. So just to clarify the notion of the box and the grid. So what I was telling you is, for example, pick up this car. Where is the center of the car? Let's say it is here in this green dot. So since the green dot falls here into this grid, this grid will have one of the boxes responsible to predicting this car. All the other grids will have boxes also, but the boxes won't matter. They won't do anything to the loss function that will be optimized. They will be hanging around here, but they are not going to count for anything. The only boxes that will count are the boxes that come from having the center here. Okay. So and how do I characterize the box? So I characterize it by saying where is the center. So by these 2 values here, they will say, okay, so the x coordinate is 0.8, so it is close to this edge, and the y is 0.9, so it is close to this edge here. BW is the width of the car, of the box, and then the BH is the height. So if I tell you the width, the height, and the center, then the box is determined. So this is what the model will output. It will output these 4 numbers that will characterize where the box is. Okay, and it will also output which class the object is. So for this problem, it is a pedestrian problem of differentiate between cars, lights, and pedestrians. So since it's a car, it will output 1 here, meaning that this is a car, 0 meaning that it's not a traffic light, and 0 meaning it's not pedestrian. Okay. Oh, okay. So this is how the grid relates to the boxes. And so here is the YOLO architecture. It looks a lot like a convolutional neural network, right? It is a convolutional neural network in the end. It has some MLP parts, like this is MLP, and then this one is also an MLP, but it's MLP organized. It is a little bit tricky. But the point is, what makes this structure YOLO instead of simply a convolutional neural network is the output. The output is the only thing that characterizes the YOLO, because the output is related to the input to put those boxes. Now I'll show you how. So here in the right, I just zoomed in this last layer here in the output. So this output is 7 by 7. Why is 7 by 7? Because there are 7 grids here and in here. So as I go over these pixels around here, I will cover information from each one of these boxes. So YOLO does 2 boxes for each cell. So this is a cell, and then it will have 2 boxes. Here I'm showing only 1, but there are 2, right? So how does it work? So all this bar that shows up here gives information about one of these cells, let's say is this one, okay? So since this cell is responsible to predicting the dog, it will have the information about the box. So meaning, where is the x coordinate, where is the y coordinate, what is the width, what is the height, and what class it is, and if there is an object there or not. Since there is a dog here, then this guy is 1. It will also have a second box floating around here, maybe also close to the dog, okay? But it will have their own coordinates. And I'll also have class probability for each one of the objects of the interest. So this is the probability of it being a dog. This is, let's say, a bicycle, and then this is a car, okay? So this is the structure. So the output is connected to these boxes. So if I pick up this bar and then put it 1 pixel to the side, then I'm referring to another cell, let's say this cell here, okay? And it will characterize different boxes during this way, okay? This is the loss function that we want to optimize. I don't want to go over details on this, but I just want to give the brief intuition about it. So what it is doing is it is putting the estimate of the x center to be close to the real x, which is specified in the data set. So in the data set, we say, okay, the center is here. So this is the x coordinate of the center. This is the y coordinate of the center. And then this is the output for the y coordinate. This is the output for the x coordinate. And we want them to be close together. So we'll optimize the loss as being, let's say, squared loss. Okay. Same thing for the width and the height. So we want them to be close together, the ones predicted and the real ones. This is the probability of there being an object there. I want, if in the data set is either 1 or 0, if there is an object or not. Okay. So if it is a 1, then we want C hat to be close to 1. If it is a 0, then we want C hat to be close to 0. And here is the probabilities of each class. So here in the data, we'll have 1, 0, 0, meaning it is a car. And we want the probabilities to be close to 1 here, close to 0 here, and close to 0 here. So this is what this summation is doing, okay? It is more complicated than that, but I just wanted to give you the basics of what the loss function is supposed to do, okay? Right. So I told you that the model gets rid of redundant boxes, okay? This is more of a detail, but since it's an important one, I will just say briefly what it is. So let's say we have these 3 boxes trying to predict the cat, okay? So the center of the cat is, let's say, here, and then, so this box is, this cell is giving me 3 boxes, okay? And I want to see if the boxes are redundant or not, okay? If they are redundant, I want to get the best one, probably the red one, okay? Which the confidence is 0.9, here the confidence is 0.7, and here is 0.8, okay? So how do we do that? So, we can calculate the intersection over union, which means this area divided by this area here combined. So intersection over union, okay? If the intersection over union is too high between 2 boxes, they are probably trying to predict the same thing. So I will just pick up the one with the highest confidence. This is how we get rid of redundant boxes. Here's an example. All these boxes around the car, they will have intersection over union very close to 1. They are equal to 1 if they are the same. And then here you have the boxes of this same object. So since all of them will have intersection over union very high, they will be shut down, and I will be outputting only one of them, the one with the highest confidence. If we do that for all pairs of boxes that have very high IOU, we get to this image here, which is much better than this one, which has lots of redundancy, okay? So this is how the model gets rid of multiple boxes predicting the same thing. Okay. All right, so it's time for seeing the results, right? So let's go again over the data set one really briefly because I already introduced it. So it is that problem of the crown of thorns, and we want to identify the starfish. So we have the image. The images are actually frames from videos. So we have 3 videos, and this many frames. Okay. So in this problem, we have images of size 1,000 by 700, I think. Let's see. Here. About 1,000 by 700. So it is very high dimensional, right? So this is more than 1 million pixels, okay? Maybe it's, well, if we multiply by 3 because it's RGB, then it's more than 1 million. So each one of them is like a covariate. So we have this very high dimensional problem. Each image has more than 1 million pixels. So it is pretty challenging because of that. Let me just go around. And if you remember, like this is the image, right? And this is one of the images in the data set, and we want to see where the crown of thorns are. Okay. So to solve this, we did it in basically 3 steps, which means pre-processing and gathering more data. So first, we did some augmentation, meaning, for example, that every image will have, we will add a Gaussian random noise to the pixels to get a slightly different image, just to augment our data set and have more examples. We also did some random horizontal or vertical flips, so that the image is like flipped in the horizontal or vertical to produce more images. We also picked up random brightness and contrast modifications, so that the training, and we concentrated ourselves into only the images with 3 or more cuts, so that we don't have many images with little cuts, right, with few cuts. Okay, it was basically a way of cutting down some of the frames that were not that interesting for the model. Okay? So we ended up with a training set like this, 1,733 frames, and this many cuts were observed. In the step 2, we increased the dimension. So we like reduced the dimension to this, and we also increased it to this, 2,400 by 2,400, to see if there was a difference. Okay. And on step 3, we augment the data, showing more images from a different data set that comes from this website called Google Starfish. So these are also cuts, but the thing is that these cuts are bigger. So let me show you. This is not from the Kaggle data set. This is from the from this one, from HoboFlow. It's the one used on step 3. Because what we did was we fit the model to the original images, which were very small. Remember, like these plots are very small. And then we try to say, okay, so do the model capture the bigger ones? Like if we go close to the starfish, what does the model do? It does what it is shown here on picture A. It doesn't recognize any of them because it's very different from what it sees. So then we were like, oh, okay, so we need to show them bigger cuts so that they can predict. And after we do this, we show this image to the model again, and the model can recognize. Okay? So this is actually from a video I will show you later, but this is from a video that were not fed to the model to train it. Okay, so this is a frame that the model has never seen before, and it could recognize the cuts. Okay, so here we can see the improvements. The higher these numbers are, the better the model is. So we see that the baseline training, after we do steps 1 and 2, it gets a huge improvement into the precision. And also, if we show more cuts, it doesn't damage the prediction to the Kaggle data set. Okay, so these precisions are all in validation set of the original data. Okay, so it is all on videos that were never shown to the model. So we see an improvement on doing these 3 steps. Okay, and then here I wanted to show you quickly these two videos so that you can get a grasp of how the model is performing. Here's the first one. Okay. So it is a little bit like fast. So you can see the red box is what the model outputs, and the green box is the truth. Okay. You can see that it is flickering, right? And there is a delay because if the cut is too far away, it's hard to detect. Okay. But once it gets close, you see it sort of captures, right? In the middle of the trajectory, the model gets a little bit confused and sometimes outputs things that are not caught. But I think it actually helps a lot, right? If I were to just pause here and then find a caught, I'll be looking for it forever, right? So the model gives us the spots that we should look more carefully to it, right? And that's the importance of also showing the bigger caught, because once you are looking for them in the sea, we want to get close to it and then confirm if it is or not. So if you get close to it and then the model doesn't say anything anymore, it's a little bit, I don't know, it's a little bit silly. So that's why we put the other data with bigger caughts. Okay. Then I want to show this one, which is the video with the larger animals. Okay, this is also never shown to the model when training. It is the model outputting the predictions to a totally new video it has never seen. Okay, so some of them are not captured. Like you see, there's lots of flickering. It is the model is not as good as predicting the big caughts as it was for the smaller ones. The reason for that is that there is much less data that were shown to the model with caughts this big. So that's why it flickers a lot. Okay. Right. So yeah, this is the idea. So the model, and this is the same model doing the prediction over the two different videos. Well, I guess if this is correct, then I'm way beyond past the time. I'm sorry. I can't stop now because the other ones is like more videos, but it's fine.
No worries, Carlos. Thank you. Great presentation. Thank you so much, Carlos. And well, now we have time for 10 minutes for questions. Let's see if anyone has a question. Okay, let's wait 5 seconds. Okay, meanwhile, I would like to ask you a couple of questions. The first one, because we met 10 years ago, if I'm not mistaken. I think it was 10 years ago. At that time, you weren't, I think you weren't familiar with these methods because of the time. And when did you begin working with these methods, using machine learning and deep learning?
Right. I started it during my PhD, because while I was working with Peter, I also was in contact with Mingo and Joe, which is another professor from UT Austin, and he was starting to look into these neural network applications. And then we had this group, this PhD group with his other students, and then we started studying this neural networks for many applications, for classification of images, for text generations. And then I started like falling in love with these models because they are, I don't know, to me they are very impressive. And then I started on a side on side projects. I started studying it, and now I do it. Like, I'm half a statistician and half a machine learning guy with these image problems.
Yeah, this is why I ask you this question, because for us as statisticians, it's really important to, at least for me, that because I'm really ignorant with these methods, I took a course of machine learning while I was doing my PhD, but I consider myself really ignorant with these methods. I asked that question because it's really important for the students who are or the people that are statisticians to differ to be aware about the differences between statistics and machine learning, and why it is important to learn these methods, and why it is important to keep statistics as statistics itself, or something different from machine learning. Because my second question is, what is do you think, because nowadays I think people in general think that you can solve anything using machine learning, but I think that is not the case, because there are still some problems that you cannot solve using machine learning. Like, for example, if you have a problem, like if you are dealing with clinical trials, for example, and I think you can use more classic or more statistic-based methods rather than using machine learning. So, from your experience as a statistician and now as a machine learning guy, what is your position? Do you think that you can solve anything using machine learning, or you need for us as statisticians, we have to keep we have to keep our world, let's say, I don't know how to put it, but try to put the barrier. You know what I mean? Just try to keep the statistics as one thing and machine learning as another thing, and recognize that statistics is still relevant. So, what is your position? Do you think that machine learning is going to be, or you can solve any problem using machine learning, and in the long term, maybe statistics is going to disappear or something like that, or is going to be absorbed by machine learning? What do you think?
This is it's a very interesting question. I think I think I think each problem begs for its own set of tools. Let's say, for example, if I want a model that is interpretable, because I want to say, okay, if there is an increase of I don't know, 1 unit of measurement in glucose level in your blood, let's say, how is that related to the probability of you developing diabetes, let's say? So I want to interpret this. I want to say, okay, this is the effect that my model estimated, and this effect ranges from blah 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 to blah blah blah. So I want to have a confidence interval or a credibility interval. So I want to interpret each one of the parameters that I quote, right? So if I want to interpret the relationship between things, then I should use like more of a statistics model, right? Because they tend to be a little bit more simple. I mean, the traditional statistical models. But on the other hand, like if I want a procedure that is able to make predictions and generalized, and I have lots of data, then I may prefer working on machine learning problems like this one with deep neural networks. But first, I think we have to recognize what the problem needs, like what sets of models the problem needs to be tackled, right? So I think both things will always coexist because the objectives are different. If I do a clinical trial, I want to estimate what is the effect of a drug into an outcome to a patient, and this will require probably simpler models, but models that we want to interpret, and we need to do this interpretation, right? So I think it varies on the problem. So, but these problems, these different models are not actually like that different. For example, the perceptron here is the same as logistic regression. It's the same thing.
Yeah,
Right?
yeah,
So
for
it
sure.
is a statistical model, So this, for me, that is the beauty of it. I think we were doing machine learning since the very beginning, but we never called it that.
Yeah, for sure, for sure. No, I think machine learning is like statistics, but when you use the statistics in a way more in a relaxed way, I don't know how to put it, or in a
Yeah,
pragmatic way, when you use.
yeah,
But I think you mentioned or you said that word, which is interpretation, and I think it leads to something more scientific, because when you are doing science, you are trying to answer hypotheses, or trying
yeah,
to prove hypotheses. So I think in that case, in the majority of the cases, you will use statistics, because statistics gives you the interpretation of the problem, the parameters. You are going to have the interpretation in the context of the problem. Whereas machine learning is something that you use more for classification and prediction. And I think I think that is the big differences between the two. But I think, as you said, I think they can coexist, and they are going to, and they are going to coexist, and for the future. And I think it is really important for the statistics for the statistics community to be aware of that. And but a final question, Carlos. Do you have recommendations of books or material for someone who were interested to begin with machine learning? Because I think from your experience, I think you maybe because you were first an statistician, and later you became a machine learning guy. So maybe you can give an advice. So how we can learn machine learning.
Okay, yeah, sure. I think, there are lots of nice references. I can show you some of them. Uh, let's see here. I would recommend for first contact a book, because these models are very complicated to understand at first by reading the papers. It's not easy, right? Because the papers are supposedly for people who already belong to the area.
Yeah.
So and there are at least a couple of pretty good books. Let me pick up like two of
Yeah,
them.
this is why I was asking that, because I think
Uh-huh.
once I just tried to learn to read an article of machine learning, but it was really difficult. Yeah.
Yeah, so this one is a really good one, I think. It is specifically based on vision systems, which is computer vision. It means uh, problems that deal with images, image classifications, image detection. It's a very good book, and I think it is very didactic. So for one that is starting, I would recommend this. If you want to go over specifically over deep learning, so neural networks and that kind of stuff. If you want something more general, then there is the book by Tibishirani, and
Ah, that's a classic. Yeah.
yeah, that one is really good. It's because I don't have
Yeah.
it here, but it is freely available on the internet.
Yeah. No,
I think it's
I know
Elements
that
of
book.
Statistical Learning. Yeah,
Yeah, it
that one.
is. Yeah, I think that was the book that I followed when I took the course of machine learning that I mentioned before. Yeah, that's the
Yeah,
book.
yeah. So this
Eh,
yellow one is a little bit more advanced. This one is also very good. This this deep learning is also for free. This is also another one in deep learning. I started with this one is by Ian Goodfellow and Bengio. They are like references in the field. It's very good. But
Okay.
this one is more of a statistical background. So
Yeah,
whoever is stats will enjoy this book. It's really nice.
yeah. It was pretty funny, because when I read that book, for me it was like, well, man, this is statistics. I don't know what is
Yeah, it
the.
is.
It's,
Agree.
it was funny, but one last question, and
Uh-huh.
about the packages for someone that is going
Oh, yeah.
to what is the best language, R or Python, or which one is the
Okay.
best for this stuff?
Okay. Well, Python is much faster. Okay. So
It's faster. Okay.
how can I put it? R is a little bit slow for loops, so if you want to program by yourself, and the problem is very complicated, like high dimensional, lots of data, then I would not try to do it in R, because R is too slow with for loops. Uh, so I would try to go for Python, but even then, like, if you just go pure Python versus pure R, it's not going to be that different. Python's going to be a little bit faster. But all these packages uh, that specifically that I did for these models and like for my students also use, they are all written in Python because they use either TensorFlow or PyTorch, which are softwares for calculating these derivatives here. Because I only have one slide for it, but it is pretty awful to calculate these
Oh yeah,
derivatives because what you have to do is calculate the derivative with respect to this.
yeah,
So in these models that are like huge, like I cannot even start writing them now. So
yeah.
the packages will calculate this by automatic differentiation, and it will speed up things a lot, especially because
Okay.
they have support to GPU, so you
Oh
can
yeah.
run it on your GPU, which is much faster than the CPU. So using the graphical processing unit, and so
Oh,
all of this is built up. So I would say it's more of a stuff like recognizing which tool you want to use. So if you want a very big problem that uses differentiation, like here with optimization, I would go for Python more than R. But if the model is simpler or if the model is already implemented by a statistician, if it is a statistical model, then I think R is going to be better because it's already implemented there first.
okay, okay. Interesting, interesting. Okay, so R is a little bit is getting behind, but anyways, anyways, Carlos, thank you so much, and yeah, I hope to have you the next time here personally, and thank you again for accepting
Oh,
the
that would be
invitation,
awesome.
and see you around, man. Thank you.
All right. Thank you. Thank you very much.
Bye. See you.
Bye bye. Let me see how I end here. Oh, okay.